unentanglement.
Okay, so, oh yeah, okay, now it's better. So yes, this talk was joint work with Sevag Gharibian at Paderborn University. And yeah, so the main theme of this talk is quantum space. And so central to that is the complexity class we introduced called QCMA space, which is a quantum analog of NP space. This is related to Savage's theorem. And yeah, so streaming proofs, because the proofs are streamed and not given in a register. And we can reduce this class to QMA2. And there's also another application is ground space traversal. So this means a mapping between two states of a Hamiltonian, two ground states of a Hamiltonian using local unitaries. So let's get started with the motivation. So everybody knows the question P versus NP, which is of course open. And another question is P space versus NP space, which is the space-bounded analog of P versus NP. And yeah, this is actually known as a Savage's theorem, so they are equal. And so just for those who don't know, NP space can be viewed as a P-space machine with access to an exponentially long stream proof. So this would look like that. You have your P-space machine. It has access to polynomial space, but it can run in exponential time. And yeah, so then you added proof. This is streamed and exponentially long, and then you get NP space. And so there are quantum analogs of NP space that have previously been studied. So the first one is a BQP space, which is was shown by Watrous that it's equal to P space. And yeah, so this is just a space-bounded BQP. So you have an exponential number of local gates, and but no streaming proof. And then you have a QMA space, which is equal to P space, shown by Pfefferman and Remskrim, and a BQP space verifier with. And this is just a BQP space verifier with a polynomial size quantum proof. And however, one might argue that a quantum analog of NP space also should have access to an exponentially long proof. And therefore, we define the complexity class QCMA space, which is a BQP space verifier with a streamed exponentially long proof. And later, I'll define in more detail what the streamed proof actually is. So let's go over our results. So the first main result is that that a QCMA space is equal to next. So this, we can say quantum Savage is false because it's not equal to P space, like NP space. And yeah, you see in contrast, we have that QMA space is equal to P space. And for our result, there's a simple proof, namely just streaming a PCP proof for next. And the second main result is the universal path following lemma, which allows us to approximately map between two quantum states along any path with exponentially long sequence of unitaries, and we have an inverse exponential error. And so one application of that would be to fool a quantum error correcting code by an exponentially long sequence of local errors, and then we can map between two code words in the ground space. And another one is the exponential time analog of GSCON with a sub-exponential gap would be trivial because then we can always map between the two states. And last main result is the embedding lemma. This allows us to reduce QCMA space to the separate sparse Hamiltonian problem with an inverse exponential promise gap. And so in the separate Hamiltonian problem, we only optimize our product states. And so the separate sparse Hamiltonian problem is known as the QMA2 complete problem. And therefore, we can also reduce multi-prover interactive proofs to QMA2. And then the promise gap is exponential in the number of bits and rounds. So next I go into detail on about the universal path following lemma. So here we have, let's say, the ground space of a local Hamiltonian. Here is a dashed line. Yeah, so and this local Hamiltonian is supposed to encode a quantum error correcting code. And you have two code words, psi0 and psi1. And now a common intuition might be that local errors will take us out of the ground space. So that would imply that there exists no sequence of local gates that map psi0 to psi1 through the ground space. But we show that this is indeed false because we can always follow any path with inverse exponential precision with an exponential number of local unitary gates. So we know that if these psi 0 and psi 1 are orthogonal, then we can always just have a continuous path through the ground space between them. And our result is that we can create a sequence of local gates that approximately follows this path. And so this part doesn't follow it exactly, so it might leave the ground space just a little bit. Yeah, so what's so special about our rotations? Because clearly they always exist in exponential length local circuit, a U that maps psi 0 to psi 1. But the problem is that normal decompositions uses like large rotations. So large means it's far from identity, like an X, Y, Z, or C naught gate. And so this would jump out of the ground space by a great amount potentially. So for example, when we map from 0, 0, 0 to 1, 1, 1, and so, for example, if we map this in the ground space, it's just the span of these two states, and then we want to apply a two local gates to get this started. So then we, for example, might apply XXI, but then we go to 1, 1, 0, which is already orthogonal to the ground space. So now I want to make this more formal. So suppose we have some polygonal path F through the points psi 0 to psi n, and the polygonal path is just the path that connects these states with line segments. Then there exists a sequence of M, which is bounded by 2 to the O of n, so exponential in the qubits, times n squared, times epsilon to the 2 minus n, so epsilon is the error term. Two local unitaries defining a polygonal path G, such that the distance between these two paths is bounded by epsilon. And so the idea is to first want to have decompose F into these small subsegments that of length with most epsilon. And then we define a rotation W, e to the IH between these subsegments and show that its spectral norm is bounded by 2 epsilon. And now we have a new lemma, which is a decomposition of small rotations. So if we have a unitary, which is e to the IH, and H is as a small spectral norm, then we can write it as a product of two local unitaries, approximately. So they have an epsilon squared error. Such that the total sum of the distance from I is bounded by some term that here is in epsilon. So, and this means that we can repeat, and because we have this epsilon squared error here, we can repeat this decomposition as often as we need it, so 1 over epsilon times, and we still have an epsilon error only. And yeah, so the maximum distance that from our intermediate subsegments is now bounded in terms of epsilon. So, I mean, it's quite a large function, epsilon to the 1 over 2n, but still it's bounded in terms of epsilon. Now, I want to sketch the proof. So this is just the lemma from the previous slide. And the first step is to write H in the Pauli basis. So these P, J are just tensor products of I, X, Y, and Z. And then we can bound this by applying Frobenius norm inequalities. And then we apply the Suzuki decomposition to write this as a product of e to the I to alpha j pj. So, and we have an epsilon squared error. Then the main part now is to decompose these I to the alpha j pj terms. So pj again is a Pauli Hamiltonian. And so we have a new lemma. So now again we have our H Pauli operator for some small t, and we also call this a pulse time. And then we can write e to the ith as a tensor as a product of e to the ith j tj. And now the hj are two local Paulis, so we have only two non-identity terms. And we need n squared of these only. And the total pulse time is t to the 1 over 2n. Now, this is lemma again, and the main ingredient here is the lemma from a paper by Clinton, Bausch, and Cubitt. And this states that if you have a unitary u e to the ith, and Hamiltonian h can be written as 1 over 2i times the commutator of h1 and h2, and h1 and h2 now anti-commute and square to identity, then we can write u like this here for some pulse times t1 and t2, such that the total, the sum of their absolute values is bounded by a square root of 2t. And this allows us to do a recursive decomposition. So now we have our Pauli Hamiltonian H, and then we write it like that. So we have H1 has the first half here. And so we assume Pj is equal to Z. Then we get in the J's term and Xj, and H2 is the second half with the Yj here. And so then we know that these, by the properties of Pauli's, they square to identity, and they also anticommute because Xj and Yj anticommute. And so because we split it in the middle, each step roughly halves the number of non-identity Pauli terms, but it increases the pulse time from t to square root t. So it's an increase because t is assumed to be a very small number, so much smaller than 1. And so this is how the recursive decomposition looks like. So here we have e to the ih, then we have the h1 terms here, and the h2 terms on the bottom. And now let's see what the applications of this construction are. So the main application is GSCON, and I define GSCON. So we're given a k-local Hamiltonian H, states psi and phi, of energy eta, and some values m and epsilon. And in the yes case, GSCON is a promise problem, so there's a yes and no case. There exists a sequence of m local unitaries that map psi to phi plus the epsilon error, such that intermediate states have energy at most eta plus epsilon. And in the no case, any such sequence must have intermediate states. So any sequence that maps psi to phi must have intermediate states of energy eta plus 2 epsilon. And here, Gharibian and Sikora show that it's QCMA complete for L equals 2, a polynomial m, and inverse polynomial error. PSPACE complete for L equals 1, and exponential m. And now in this paper, we show that if we have GSCON with exponential m, but now 2 local unitary, but sub-exponential error epsilon, then there are no instants for large n. So then the problem becomes trivial, in fact. And the proof is to apply our universal path decomposition lemma to some path from psi to phi through the low energy space. And now, in contrast to that, we also show that if we allow an exponential epsilon, then the problem is PSPACE hard. But we don't know exactly the upper bound. Best upper bound is an exp for this. And so the question one might also ask is, does the large m, would this also trivialize the L equals 1 case? Because, yeah. So, but this is not the case. And we show that GSCON with an unbounded m and L equals 1 is still PSPACE complete. And now the next main result I want to go over is the embedding lemma. And before that, I review the Feynman-Kitaev circuit to Hamiltonian construction. And here the idea is to reduce a QMA instance to a k-local Hamiltonian instance by constructing a Hamiltonian H whose ground state encodes the application of the verifier's gates one by one, and we call this the history state. So psi hist is then the superposition of all these terms. So for time step t, we have here the proof psi and the ancillars initialized to 0, and then the first t gates are applied to that. And we define now this Hamiltonian H as a sum of 3 terms. The first one being H in, so this is the initialization term, and at time step 0, it forces all ancillars to be 0. And then at time step m, we have the output term, and it penalizes a rejecting computation. So this is the output bit, and yeah, so we want the accepting, so 1. And then we have the propagation term. This is a sum of t terms, ht, that ensure that vt is applied from step t minus 1 to step t. So here we have vt from t minus 1 to t, and the reverse from t minus 1, from t to t minus 1, we have the reverse. And then we have this term here, and that makes it a nice projecture. And yeah, so it's known that this can easily be made FLUX local, and there are also further papers that improve this more. And the ground state is psi hist for some accepting psi here. Now, how does this apply to QCMA space? So here we need to go over the proof formalism now. So we have the streaming proof. We want to stream some proof y of length m. And so we do this like so. So we have 3 registers, an input register here, x, ancillars initialized to 0, and the proof register. It's a single bit only. And this operates in 2 phases. First, we have a computation phase that applies a sequence ui to the input and ancillar space. And we have a proof phase, and this sets a proof register with wi, which is x if the yi and yi minus 1 differ. So this just flips the proof bit, the proof register to the correct proof bit if necessary. And then we have a C0 gate to copy it to the insular. But now how do we embed these streaming proofs into a history state construction? So here the first idea is to move the proof out of the register and into the superposition over the time steps. And so again, we would have a history state with an insular A, proof bit B, and time step C. So, and you can see now the proof is just initialized to 0, and the actual computation is hidden in these, the actual proof is hidden in these gates. So yeah, so it's implicitly encoded into the time steps. And we divide these gates into the proof gates, which are either an I or X, but they are not predetermined, and the computation gates. And of course, the challenge is that hprop from the previous slide needs to know all gates in advance to construct it. And yeah, so but now our main question to solve is how can the history state encode the future? And for that, we introduce the FLUX gadget by asking the question, what if we allow two parallel worlds? And in our case here, parallel worlds means that we now not look at normal Hamiltonians, but we look at separate Hamiltonians where we can basically have two history states in parallel. And we allow both worlds to choose whether they apply I or X. And then we have a Hamiltonian term like this. So this is basically the FLUX gadget term. And this is here our transition term from above. We just replace the VT with either an I or X. And we want that this term enforces that both worlds apply the same gate. Yeah, so that the gate is not fixed a priori, but we force it to apply the same gate. And this term basically is supposed to simulate a Boolean function, Boolean equality function like that. And we want that its low energy state is the history state on both registers for some accepting proof y star. But unfortunately, this construction is not sound, because if we just initialize the proof bit to a plus, then these terms are both annihilated, because the x and I act the same as in the plus. And our fix is to use an ix, so we make it complex instead of an x. And now we can define this FLUX gadget. So again, we define the complete Hamiltonian. We have an h in, h prop, and h out. And so both are very similar. So this is the sum of two terms. The first one acts on the left subspace, and the second one on the right subspace. And in the propagation term, we make an exception for the how's it called? For the proof gates. So here we actually have our FLUX gadget now inserted. And what's doing that? And now notice that we have an ix here and not an x anymore. But this construction is still not sound, because now we can have a state like this. So here the left register only has support on the last time step, and the right only on the first time step. So the L register annihilates all time steps but the last, and R all time steps but the first. So in total, we are in the null space. And the fix is to enforce symmetry by having this H-sim term, which is I minus the projector into the symmetric subspace. And we know that if H-sim times psi L psi R is equal to 0, then they must be equal. So if we then later we need to adjust the weights suitably. So if we make the weight large enough, then we can assume in our proof that they are equal. And yeah, so we note that H-sim is not local but sparse. So we don't. So therefore we have to use the separate sparse Hamiltonian problem. Okay, that's that. And so let's now state the embedding lemma. So we have a quantum verifier Q given of length m with a classical streaming proof y of length 2 to the p, with m at least 2p, 2 to the p. We have Q ancillars and thresholds alpha minus beta larger than 2 to the minus r. And then we can reduce Q to a separate sparse Hamiltonian instance H on Q plus log m qubits. So the number of qubits is logarithmic in the number of in the proof length, with thresholds alpha prime and beta prime is omega of 1 over 2 to the r times m. So the longer our proof is, the smaller our thresholds we have to use this. And from this, we get the corollary that we can reduce the QCMA space with proof length P and Q and Silas to a separate sparse Hamiltonian problem. And again, with a gap 2 to the minus P minus R. Another corollary, OK. So can I? OK, and we get also an application to GSCON, which is next complete. So we have a version of GSCON that's not next complete, but we require a sparse Hamiltonian, inverse exponential promise gap, and exponentially many 2 local gates that are now required to not cross a given LR cut. So let me very quickly conclude with open problems. So we have a GSCON with exponential length and 1 over exponential gap, which we know is between P space and next, but can we get a tighter bound? So I just mentioned a version of GSCON that is next complete, but we don't know for this normal one. And so the embedding lemma, can we have more choices of gates? Because our construction only works for the I and X gate choice, but can we allow it to stream arbitrary gates? And the embedding lemma recovers the result of Bleer and top, that NP has a log size QMA2 proof with 1 over poly gap. So we also recover that result, but can it improve to constant gap? Thank you for listening.
All right, we have time for questions. If you want to ask a question, please line up here. Maybe I'll start. So is it true that according to your definitions, QCMA space is bigger than QMA space?
It's bigger. What do you mean with bigger? We show that it's equal to next, but QMA space is equal to P space.
Right. So QCMA space contains QMA space, like somewhat non-intuitively, because usually QMA contains QCMA. Right.
Yeah, but yeah, the formalism is a little bit unintuitive. The naming maybe.
Okay. Yeah, just checking. Right. Other questions?
I have a dumb question. So for higher dimensional Hilbert space, I saw the proofs sounds like using qubits.
Sorry, I didn't understand your question.
Like for QDIS, higher dimensional Hilbert space.
You mean if we have qubits and not qubits?
Yeah. That's it. Is it included in the second open question or open problems? So I think the gate choices. I don't know if you use similar proofs or is it included in the open problem?
I'm so sorry. I totally don't understand your question acoustically.
Yeah.
We can maybe talk later if you want. Just an instant.
Hi, so I guess I had a question related to Robin's question. Is there a notion of QMA space with a streaming quantum proof that would by definition contain QCMA space? And with that class, do you know anything about that class, if it makes sense?
You could stream it. You could, right now we stream classical bits. You could also stream quantum bits, I suppose, which would include QCMA space. But that class would maybe be much more powerful, but I don't know how powerful it is. But it's not, at least it's not necessarily included in next.
I see. Thanks.
All right, let's thank the speaker again. Yeah.